Welcome back. In this video, you'll learn about the binomial series. Let's get to it. Alright, so the binomial series is a special type of Maclaurin series that results from finding the Maclaurin series for this function right here. F of x is equal to the quantity 1 plus x to the power of k, where k is some real number. Alright, so this could be 1 plus x squared, or 1 plus x to the power of negative 2, 1 plus x to the 1/2 power, the 3/2 power. Any real number can be the value of this power k. Okay? And so when we represent this function as a Maclaurin series, no matter the value of that power k, we are going to find the binomial series. Now remember, a Maclaurin series is just a Taylor series that is centered at 0, and it looks like this. We have the sum from n equals 0 to infinity of the nth derivative of our function evaluated at 0 divided by n factorial times x to the power of n. Okay, so what we're going to do here is find the binomial series by representing this function as a Maclaurin series. And in order to do that, we need to find the nth derivative of our function evaluated at 0. Okay, so the first thing we want to do is find that nth derivative, and then we'll worry about evaluating it at 0. Okay, so to find that nth derivative, we need to start taking derivatives of this function. And so let's start by finding the first derivative, f prime of x. F prime of x will be equal to the derivative of 1 plus x to the power of k. And now this is going to require the power rule for derivatives as well as the chain rule, right? We have an outside function of this quantity to the power of k, and then we have an inside function of 1 plus x. Now we'll use the power rule for derivatives on the outside function. So we multiply the power down and then subtract 1 from that exponent. So we'll have k times 1 plus x to the power of k minus 1. All right, and then we want to multiply by the derivative of that inside function. But the derivative of 1 is 0 because 1 is a constant, and the derivative of x is just 1. And so we just be multiplying by 1. And that's not going to change the value of this derivative, so we don't even need to worry about multiplying by the derivative of that inside function. From here on out, as we take our higher order derivatives, we're just going to use the power rule for differentiation on this quantity, and we're not going to worry about multiplying by the derivative of the inside function. Okay, so this is our first derivative. We have k times the quantity 1 plus x to the power of k minus 1. Now if we take a second derivative, f double prime of x will be equal to this power multiplied down, and then we'll subtract 1 from that exponent. So we'll have k times k minus 1 times 1 plus x to the power of k minus 2. We subtract another 1 from that exponent, so k minus 1 is k minus 2. And now let's find the third derivative. F triple prime of x will be equal to this power multiplied down, and then we'll subtract 1 from that exponent. So we'll have k times k minus 1 times k minus 2 times 1 plus x to the power of k minus 3. Okay, and now let's do one more derivative. Let's look at the fourth derivative of our function. That will be equal to this exponent multiplied down, and then we'll subtract 1 from that exponent. So we're going to have k times k minus 1 times k minus 2 times k minus 3 times 1 plus x to the power of k minus 4. All right, so maybe you're starting to see the pattern of what is occurring with each derivative of this function. And so at this point, I think we're ready to express the nth derivative in terms of n from the pattern that we see with these derivatives. Okay, and so how can we represent the nth derivative of our function? Well, let's start by looking at the coefficients of these derivatives. Ignoring the 1 plus x to the power of k minus 1, or 1 plus x to the power of k minus 2, and so on, let's just focus on these coefficients in front of that quantity. For the first derivative, we just have k. For the second derivative, we have k times k minus 1. For the third derivative, we have k times k minus 1 times k minus 2. And then for the fourth derivative, we have k times k minus 1 times k minus 2 times k minus 3. Now in terms of the nth derivative, we would say that the first derivative is when n equals 1, the second derivative is when n equals 2, the third derivative is when n equals 3, and the fourth derivative is when n equals 4, right? So notice that the last quantity of the coefficients is k minus a value that is 1 less than the value of n, right? For the fourth derivative, we have k times k minus 1 all the way up till k minus 3, and 3 is 1 less than 4. For the third derivative, we have k multiplied by k minus 1 times k minus 2, and 2 is 1 less than 3. For the second derivative, we have k times k minus 1, and 1 is 1 less than 2. And then for the first derivative, we have just k, which you could say is k minus 0, and 0 is 1 less than 1. So we could represent our coefficients like this. We're going to have k times k minus 1, and then we're going to continue to multiply by quantities until we get to k minus n minus 1. One value less than n. All right, that is the pattern that we see with our coefficients. We just keep multiplying these quantities until we get to k minus the quantity n minus 1. All right, now we can simplify this a little bit. If we distribute this negative through this quantity, we'll have k minus n plus 1. So I'm just going to rewrite this, and we'll have k minus n plus 1. All right, and so that takes care of our coefficients, but then what about our quantities of 1 plus x? How can we represent their powers in terms of n? Well, notice that for those quantities in each derivative that we have k minus the value of n, right? For the first derivative, we have k minus 1, and n equals 1 for the first derivative. For the second derivative, we have k minus 2, and 2 is the value of n for the second derivative. And then for the third derivative, we have k minus 3, and the third derivative is when n equals 3, and so you can sort of see the pattern. K minus 4 for the fourth derivative is when n equals 4. So we can express that quantity in terms of n as 1 plus x to the power of k minus n. All right, whatever that value of n is, we're going to subtract that from k. All right, and so what we have right here is the nth derivative of our function f of x. For any nth derivative, whether that be the third derivative, the fourth derivative, the fifth derivative, and so on, we can plug that value of n that corresponds to that derivative into this expression to find that derivative. So if we wanted to find the seventh derivative, n would be equal to 7, and so we would multiply out these coefficients until we get to k minus 7 plus 1, which would be k minus 6. All right, and then we'd multiply by 1 plus x to the power of k minus 7. All right, so that's how this nth derivative works. But now, we want to evaluate this nth derivative at 0 in order to write out the Maclaurin series for this function. So, if I clean up my work, let's evaluate our nth derivative at 0. Our nth derivative, evaluated at 0, will be equal to k times k minus 1, multiplying all the way up till k minus n plus 1 times 1 plus x, which is 0, to the power of k minus n. All right, so that x right there is the only x in this nth derivative, so that's the only place where 0 gets substituted in. Now 1 plus 0 is 1, so what we have here is just 1 to the power of k minus n, but 1 to the power of anything that's finite, which in this case, this would be finite. It's not going to be infinity or negative infinity. 1 to that power is just going to be 1. All right, so this whole thing just becomes 1, and 1 times any value is just going to be that value, so the nth derivative, evaluated at 0, is just equal to the coefficients of that nth derivative. All right, so now that we know what the nth derivative evaluated at 0 is, we can replace that in the Maclaurin series with this expression, and we will have the Maclaurin series for this function f of x. So what we'll have is that f of x is equal to 1 plus x to the power of k, which will be equal to the sum from n equals 0 to infinity of the nth derivative evaluated at 0, which is k times k minus 1, multiplied up until k minus n plus 1, and that will be divided by n factorial, and then we multiply by x to the power of n. What we just found right here is the binomial series. This is the Maclaurin series that represents this function, and we call it the binomial series. And the reason why we call it that is because this series would actually give you the binomial coefficients if you're familiar with binomial coefficients. If not, don't worry about that too much. In this case, you just want to be aware of what the binomial series is so that you can use it to represent functions of this form as a power series. Okay, but if you are interested in what this binomial series actually does, feel free to do a little bit of research on binomial coefficients, as you might find that information to be helpful in terms of why we call this the binomial series. Okay, but that's not the focus of this video. We want to focus on using this binomial series to represent functions as power series, or more specifically as Maclaurin series, because the binomial series is just a special type of Maclaurin series. Okay, and so now that we found the binomial series, let's take a look at what some of the terms of this series would look like. So if I clean up my work here, let's start by writing our first term when n equals 0. Now remember, this is a Maclaurin series, so the first term of the series is just going to be f of 0. So we're not going to plug 0 as our value of n into this expression. Instead, just remember that the first term of your Maclaurin series is just what results when plugging 0 into your original function. So in this case, we have 1 plus 0, and 1 plus 0 is 1 to the power of k is just going to be 1 because 1 to any finite power will be 1. So our first term is just going to be 1. And that will be true for all binomial series. All right, and now for the rest of our terms, we can plug in our values of n into this expression. Okay, so our next term is when n equals 1. And so we're going to be multiplying these coefficients until we have k minus 1 plus 1. Now, minus 1 plus 1 is 0, so we're just going to be multiplying up to k. So our only coefficient will be k, and that's going to be multiplied by x to the power of 1, and that will be divided by 1 factorial. Now, 1 factorial is just 1, and x to the first power is just x, and so we can rewrite this to just be k times x. So we'll have k times x. Then we'll add that to our next term when n equals 2. In this case, we're going to be multiplying these coefficients until we get to k minus 2 plus 1, or we're going to be subtracting a value that is 1 less than our value of n, right? So we're going to have k minus 2 plus 1, which will be k minus 1. So we're going to have k times k minus 1, and then we will stop and have x squared because n is equal to 2, and then we'll divide by 2 factorial. Now, hopefully you can start to see the pattern that's occurring here. The next term is going to be k times k minus 1 times k minus 2 times x cubed divided by 3 factorial, right? N would be equal to 3 for this term, so we're going to multiply k times k minus 1 times k minus 2 and stop there because 2 is 1 less than 3. And then we have x cubed divided by 3 factorial. All right, so we could continue to add on more terms from there. When n equals 4, we'll have k times k minus 1 times k minus 2 times k minus 3, then x to the fourth power divided by 4 factorial, and then you could keep on adding more terms from there. All right, so these are what the terms of the binomial series look like. The actual value of the terms is going to depend on what the value of k is, which is the power of that function, right? 1 plus x to the power of k, that value of k determines what these terms will look like for a particular series. All right, so to summarize, this is the binomial series. F of x is equal to 1 plus x to the power of k. When we represent this function as a Maclaurin series, it looks like this, and we call it the binomial series, where we have k times k minus 1, then we keep multiplying until k minus n plus 1, and we divide by n factorial and multiply by x to the power of n. And then, of course, these are the first couple terms of that series, which is honestly the most important part for you to remember. Understanding the structure of the terms of the binomial series is going to be very important to know in order to use the binomial series to express functions of this form as a Maclaurin series. All right, and so this is the binomial series, but one more thing that we have to remember to check here is what is the interval of convergence for this power series? What values of x is this power series convergent for? Right? Because this function, f of x, or more specifically 1 plus x to the power of k, is only defined for the values for which this power series is convergent for. So we have to know what values of x it will be convergent for. All right, and as it turns out, the convergence of the power series, or the interval of convergence, is completely dependent on the value of k. It's all determined by what that power is for this function. All right, and so here's what you need to know about determining the interval of convergence for a binomial series. If that value of k is a positive integer, meaning values like 1, 2, 3, 4, 5, and so on, write the whole numbers greater than 0. If k is a positive integer, then the binomial series will be convergent for all values of x, from negative infinity to infinity. But if k is not a positive integer, so that could be -1, that could be 1/2, because 1/2 is positive but not an integer. 1/2 is not a whole number, and so anytime k is not a positive integer, the interval of convergence will at least be from -1 to 1. However, it could change if one of these other two requirements is met. If k is between -1 and 0, then the interval of convergence will change to include that endpoint of 1. And if k is greater than or equal to 0, then the interval of convergence will include both of those endpoints. All right, so for a couple examples, let's say k is equal to 2. 2 is a positive integer, so that function would result in a binomial series that converges for all values of x. If k was equal to -2, then k is not a positive integer, it's a negative integer, and -2 is not between -1 and 0, and it's not greater than or equal to 0, so that value of k would result in this interval of convergence from -1 to 1, not including those endpoints. Now let's say k was equal to -1/2. If k is -1/2, it's not a positive integer, and it's between -1 and 0. -1/2 lies between those two values, so this would be the interval of convergence. All right, but if k was +1/2, it's not a positive integer, but it is greater than or equal to 0, and so when k is 1/2, this would be our interval of convergence. All right, so hopefully that makes sense. That is how you determine the interval of convergence for a binomial series, depending on what the value of k is. All right, and so with that, we are ready to look at our first example of using the binomial series to represent a function as a Maclaurin series. Okay, so here's our first example. We want to use the binomial series to find the Maclaurin series for f of x is equal to 1 divided by 1 plus x quantity squared. All right, now this function might not initially look like it's in the correct form, right? Remember, the binomial series represents a function f of x is equal to 1 plus x to the power of k. But if we move this quantity to the numerator and make that exponent negative, then our function will look like this. We'll have f of x is equal to 1 plus x to the power of -2. And now our function is in this form that can be represented by the binomial series. Okay, so in this case, we would say that k is equal to -2. And remember from our rules for the interval of convergence, since this value of k is not a positive integer, and it's not between -1 and 0, and it's not greater than or equal to 0, k equals -2 means that the series that we find for this function will be convergent from -1 to +1, not including the endpoints. Okay, so keeping that in mind, let's now work on representing this function as a Maclaurin series by using the binomial series. And so remember, when you have the function of this form of 1 plus x to the power of k, these are what the terms of the binomial series will look like. And this is what we're going to use to find a pattern within our terms that we will then express as a power series, which will be a binomial series, and it will also be a Maclaurin series. Okay, so these are the terms that we're going to use to make that happen. So in this case, k is -2, so our function will be equal to 1 plus -2 times x, right? We have 1 plus k times x. Then we're going to add this to k, which is -2, times -2 minus 1, or k minus 1, times x squared divided by 2 factorial. Then we'll add this to k, which is -2, times -2 minus 1, times -2 minus 2 times x cubed. And that will be divided by 3 factorial. All right, and then we can continue to add on more terms from there. But now what we want to do is simplify. And so if we do that, we will have that this is equal to 1 minus 2x, right? We are adding -2x. So instead of having plus -2x, we're just going to subtract 2x. And this is added to -2 times -3 times x squared divided by 2 factorial. And then we're going to add this to -2 times -3 times -4 times x cubed divided by 3 factorial, and we can continue to add on from there. Now, I didn't actually multiply these coefficients together Because remember, what we want to do is determine a pattern for these terms that we can then represent as a power series, or more specifically, a binomial series, which would be a Maclaurin series. All right, so I'm not going to multiply these coefficients together, but what I will do is make a note of the sign of these two terms. All right, so we have -2 times -3. Those two negatives will cancel out, so we're going to have a positive term here. And so we could remove those negatives, and what we'll have is just 2 times 3 times x squared. So we'll have 2 times 3 times x squared. And then for this term, we have -2 times -3 times -4. That's 3 negative signs, so 2 of them will cancel out, and then the third one will make this whole term negative. All right, so instead of having -2 times -3 times -4, let's just subtract this whole term and have 2 times 3 times 4 times x cubed. Okay, so I'm going to erase all of this, and what we're going to have instead is 2 times 3 times 4 times x cubed, and then we're going to subtract that term. Okay, and so now we can start to see what the pattern is going to be for these terms. What I want you to notice is that for these two terms and every term after that, we're going to have some cancellation. In the numerator, we have 2 times 3, which you could also view as 1 times 2 times 3, and 1 times 2 is 2 factorial, right? So 1 times 2 and 2 factorial will cancel out. And then in this term, we have 2 times 3 times 4, which would be the same as 1 times 2 times 3 times 4. And so 1 times 2 times 3 is the same as 3 factorial, and so that's going to cancel out. And this is going to occur in every single term. If we were to look at the next term, in our numerator, we would have 1 times 2 times 3 times 4 times 5, and in the denominator, we would have 4 factorial, and 1 times 2 times 3 times 4 would cancel out with that 4 factorial and just leave us with 5 times x to the 4th power. All right, so that would be our next term. But in every single term, we're just going to be left with one coefficient and then x to the power of n. All right, so if I clean up my work, after we make these cancellations, what we're going to be left with is 1 minus 2x plus 3x squared minus 4x cubed, and so on. In fact, I'll write another term just so you can sort of see what's happening. Our next term would be 5 times x to the 4th power. Then we would subtract 6 times x to the 5th power, and so on. All right, because with our previous terms, you can see that they are alternating between being positive and negative, and so that pattern will continue on for the rest of the terms. And then we just increase the coefficient of the terms by 1 each time, and we're also increasing that power of x by 1 each time. Okay, and so now we can clearly see the pattern that is happening with these terms that we can now represent with a Maclaurin series. So I'll clean up my work one more time. This is going to be equal to the sum from n equals 0 to infinity of -1 to the power of n, right? This is going to ensure that each of our terms alternate between being positive and negative, like they are right here. And we have -1 to the power of n, because since we're starting with 0, -1 to the power of 0 will be +1, which will ensure that our first term is positive. All right, if our first term was negative, we would want this to be -1 to the power of n plus 1, so that we would have -1 to the power of 1 when n equals 0, and that would make that first term negative. But since it's positive, we want -1 to the power of just n. All right, and then we know that the coefficients of our terms are just the value of n plus 1. Right, this first term is when n equals 0, then we have n equals 1, n equals 2, n equals 3, n equals 4, and so on. And what you can see is that the coefficient of each term is 1 greater than that value of n. Right, when n equals 0, the coefficient is 1. When n equals 1, the coefficient is 2. n equals 2, the coefficient is 3, and so on. So we're going to multiply -1 to the power of n times n plus 1. And then all we have left to take care of is this x that is raised to a power. And in each case, we have x raised to the power of n. For the first term, you would have x to the power of 0, which is just equal to 1. So 1 times 1 is 1. Then for this term, we have x to the first power. Then we have x squared for n equals 2, x cubed for n equals 3, and so on. So our last part of our series will be x to the power of n. And so this power series is a Maclaurin series, and it's also a binomial series that represents this function of 1 plus x to the power of -2, or you could write it as 1 divided by 1 plus x quantity squared. All right, and we already determined from that value of k that this power series will be convergent on this interval from -1 to 1. Okay, so we'll say that this series represents this function on the interval from -1 to 1. And that is the final answer to this example. We have found the Maclaurin series that represents this function by using the binomial series. Okay, and so now let's take a look at one more example for this lesson video. All right, so here's our second and final example for this video. Just a quick heads up, this is going to be a little bit more complex than the previous example. A lot of times these types of examples where you want to use a binomial series to represent a function as a Maclaurin series can be pretty involved in terms of trying to identify a pattern for your terms from the binomial series that would then be used for the Maclaurin series. All right, but we're going to take this step by step, and if any part confuses you along the way, be sure to leave a comment below. All right, but the first thing that we want to do is identify the value of k for the function we're working with. And in this case, we're using the binomial series to find a Maclaurin series for this function where we have f of x is equal to the square root of 1 plus x. All right, now we can rewrite that square root to be the power of 1/2. So this function is really f of x is equal to 1 plus x to the power of 1/2. So we have 1 plus x to some power k, which means that k is equal to 1/2. Now from our list of rules from earlier, dealing with the intervals of convergence, when k is not a positive integer, and it's not in this case, k is equal to 1/2, that is not an integer, but it is greater than or equal to 0, right? Since k is greater than or equal to 0, and it's not a positive integer, that means that our series will converge on the interval from -1 to 1, including both of those endpoints. Okay, so this will be the interval of convergence. I'm kind of jumping the gun here. We didn't need to really find that right away, but I like to take care of that right at the beginning so that now we can just focus on finding our Maclaurin series and just tack on that interval of convergence at the end. You don't want to forget to find that interval of convergence, so identifying what that's going to be first might help you not forget to determine what it will be. Okay, but now with that, let's start writing out the terms of the binomial series that would represent this function. Okay, so remember, when you have 1 plus x to the power of k, these are the terms that we're going to be working with. So our function is going to be equal to 1 plus k times x, which will be 1/2 times x, plus k, which is 1/2, times k minus 1, which will be 1/2 minus 1 times x squared, divided by 2 factorial. Then we're going to add that to k, which is 1/2, times k minus 1, or 1/2 minus 1, times k minus 2, or 1/2 minus 2, times x cubed, divided by 3 factorial. And I'm going to write another term yet. I think it's going to be helpful if we look at 5 terms here. So we're going to add this to 1/2 times 1/2 minus 1, times 1/2 minus 2, times 1/2 minus 3, times x to the 4th power, divided by 4 factorial, and then we can continue to add more terms from there. All right, so now what we want to do is simplify each of these coefficients. So we're going to subtract 1 from 1/2, subtract 2 from 1/2, and 3 from 1/2, and then we're going to see if we can identify a pattern of some kind within our terms. Okay, so this will be equal to 1 plus 1/2 times x plus 1/2 times 1/2 minus 1. That will be negative 1/2 times x squared divided by 2 factorial. Then we're going to add that to 1/2 times negative 1/2. And then 1/2 minus 2 is negative 3/2, right? 2 would be equal to 4/2. So 1/2 minus 4/2 is negative 3/2. So we have negative 3/2. And then that's multiplied by x cubed divided by 3 factorial. Then we'll add this to 1/2 times 1/2 minus 1, which is negative 1/2, 1/2 minus 2, which is negative 3/2, and then 1/2 minus 3 will be negative 5/2, because 3 is 6/2, so 1/2 minus 6/2 is negative 5/2. All right, then we multiply by x to the 4th power and divide by 4 factorial and add more terms from there. Okay, now just like with our other example, the next thing that I recommend you do is try to figure out what's going on with the sign of each of your terms. We know that the first 2 terms are positive, but if we look at our second term here, we have 1/2 times negative 1/2. So this whole term will become negative. So what I'm going to do is erase this plus out front, make it negative, and then just have 1/2 times 1/2 in the numerator. So both of those 1/2s are positive. Then for our next term, we have 1/2 times negative 1/2 times negative 3/2. And so those two negatives will cancel out. So this whole term is just going to be positive. So I'm going to rewrite this to be 1/2 times 1/2 times 3/2. And those will all be positive values. So we'll have 1/2 times 1/2 times 3/2. And that's all multiplied by x cubed. All right. And then for this term, we have 1/2 times negative 1/2 times negative 3/2 times negative 5/2. We have three negative signs. So two of those are going to cancel out and be positive, and then that third one is going to make the whole term negative. So I'm going to erase this plus sign, make that term negative, and then rewrite all of these values to be positive. So we're going to have positive 1/2, positive 3/2, and positive 5/2. So 1/2 times 1/2 times 3/2 times 5/2 times x to the fourth power. Okay, so we're getting closer to being able to identify a pattern. What I want to do now is simplify these numerators, not by multiplying the values together. That would defeat the purpose of trying to find a pattern. Instead, I'm just going to move these denominators to the actual denominator, right? We could pull these two 1/2s out to the front and multiply them by the whole fraction, and those two 2's would be in the denominator. All right, and we could do the same thing for the rest of these terms as well. The numerators of the fractions will stay in the numerator, and then the denominators will go to the denominator. Okay, but notice that those denominators are all 2, and it increases by 1, 2 with each term, right? We have 2 times 2, that's 2 squared. Then we have 2 times 2 times 2, which is 2 cubed. And then we have 2 times 2 times 2 times 2. That's 2 to the fourth power. So here's how we can rewrite these terms. This will be equal to 1 plus 1/2 times x minus 1 times x squared divided by 2 squared times 2 factorial. Then we'll add that to 1 times 3 times x cubed divided by 2 cubed times 3 factorial. Then we'll subtract the next term of 1 times 3 times 5 times x to the fourth power divided by 2 to the fourth power times 4 factorial. And we'll add more terms from there. All right, so all I did there was keep the numerators of our fractions in the numerator of each term, and then move those denominators, which was just 2 to some power, to the denominator of the whole fraction. All right, so now we can start to see the pattern that is developing here. Starting with this third term, our terms are alternating between being negative and positive, right? Because the first two terms are positive, so they're not really a part of the pattern that's going on here. But starting with that third term, we go from negative to positive to negative to positive. And then in the numerator, we have 1 times x squared, then 1 times 3 times x cubed, then 1 times 3 times 5 times x to the fourth power. Now we can actually ignore that first 1 that's being multiplied in those numerators, right? That 1 doesn't actually affect the value of those numerators. Neither does this one, but noticing that that 1 is there will help us identify the pattern within these terms. All right, now if I clean up my work here, let's start to put together the Maclaurin series that will represent these terms. And I'm not going to include these first two terms within that Maclaurin series. What I'm going to do is just say that this is equal to 1 plus 1/2 times x plus the sum from n equals 2 to infinity, and that's going to start our Maclaurin series that represents these terms. Right, we're starting at n equals 2 because these first two terms are when n equals 0 and n equals 1. I'm just going to leave those out because the pattern that I see for these terms starts with this third term. I'm not going to worry about including those first two. We can just represent the rest of the terms starting with the third term when n equals 2. All right, and so what I see so far is that in the denominator, we have 2 squared times 2 factorial, then 2 to the third power times 3 factorial, then 2 to the fourth power times 4 factorial, right? If this term is when n equals 2, this term is when n equals 3, this term is when n equals 4, you can see that the power of 2 in the denominator is dependent on that value of n, and the value of the factorial is also dependent on that value of n. So far we can write this. We'll have the sum of some rational expression where we will have 2 to the power of n in the denominator times n factorial. That's what we know so far. but now we need to find out what goes in the numerator. And let's take care of the easy part. We know our terms are alternating between being negative and positive, right? We start with a negative term for n equals 2, then we have positive n equals 3, negative n equals 4, and that will continue on from there. So since our first term is negative, we're going to have negative 1 to the power of n plus 1 in the numerator of our series, right? If n equals 2, we'll have negative 1 to the power of 2 plus 1, which will be negative 1 to the power of 3, and so negative 1 to the third power is negative 1, which ensures that that first term will be negative, and every other term from there on will alternate in the correct way. All right, so now we took care of the sign of our terms. The next thing I noticed that's easy to recognize is that we have x to the power of n, right? We have x to the power of 2 for n equals 2, x to the power of 3 for n equals 3, and x to the power of 4 for n equals 4. So I'm going to include x to the power of n on the end of this series. And I'm going to leave some space here because we still need to represent the coefficients of those x to the power of n parts, right? For this term, we have 1, then we have 1 times 3, then we have 1 times 3 times 5. It sort of looks like a factorial, but it's not quite a factorial, right? Instead of having 1, then 1 times 2, then 1 times 2 times 3, we're not multiplying by the next number, we're multiplying by the next odd number. So it's a little bit more difficult than writing it out as a factorial. And so the easiest way to go about this is to try to determine what that last value is that we are multiplying by, right? So we start out with the last value being 1, then we have 1 times 3, 3 is the last value we multiply by, then we have 1 times 3 times 5, and so 5 is the last value we multiply by. What we want to do is determine a sequence to represent that. Okay, so here's what I'm saying. When n equals 2, that last value is 1. When n equals 3, that last value is 3. And when n equals 4, that last value is 5. What we have here is an arithmetic sequence, right? An arithmetic sequence is just a sequence that increases or decreases by the same value with every term. We have 1, then we have 3, which is 2 more than 1. Then we go from 3 to 5, which is 2 more than 3. So every value is just increasing by 2. That is how we find that last value that we're multiplying by for our coefficients. And so what we want to do is find a way to represent that pattern in terms of n. And so since we recognize this to be an arithmetic sequence, and by the way, some people say arithmetic, just know that that's the same thing, arithmetic, arithmetic, however you say it, it's the same concept. But what we want to do here is represent that sequence. And so in order to do that, you need to know the formula for representing an arithmetic sequence. And it looks like this. The arithmetic sequence a sub n is equal to the first term a sub 1 plus n minus 1 times the common difference. All right, so in this case, when n equals 2, that would be a sub 2, n equals 3 is a sub 3, and n equals 4 would be a sub 4. And so we need to know what a sub 1 would be. And we're not going to look at our previous term because we're not including that within our power series. Instead, we're just going to follow the pattern here. Each term increases by 2. So that means when n equals 1, we would have negative 1, right? Negative 1 plus 2 is positive 1. All right, so a sub 1, this right here, will be negative 1. Our common difference is 2. Each term increases by a value of 2. And so we will have that a sub n is equal to negative 1 plus n minus 1 times 2. Now 2 times n is 2n, and 2 times negative 1 is negative 2. So what we'll have is that a sub n is equal to negative 1 plus 2n minus 2. And now negative 1 and negative 2 will combine to give us that a sub n is equal to 2n minus 3. And so 2n minus 3 represents the value of that last value that we're multiplying by for our coefficients. All right, so for example, when n equals 2 for this term, we'll plug 2 in for n, and we'll have 2 times 2, which is 4, minus 3. That gives us 1. That's what the last value will be. For n equals 3, 2 times 3 is 6, minus 3 is 3. So we have 1 times 3 for n equals 3. 3 is where we're going to stop. Then for n equals 4, we'll plug in 4. 2 times 4 is 8, minus 3 is 5. So we have 1 times 3 times 5. We stop at 5. Now I don't have the n equals 5 term written, but when n equals 5, we'd have 2 times 5, which is 10, minus 3, which is 7, which would be the next odd number. So we would have 1 times 3 times 5 times 7 times x to the 5th power for n equals 5. Okay, so 2n minus 3 represents the value of that last coefficient. And here's how we're going to express that in our series. We're going to have 1 times 3 times 5 and then multiply all the way up until 2n minus 3. Okay, so depending on the value of n, that might not include 3 or 5, such as the term for n equals 2, but we still want to represent the multiplication that is happening there. All right, so we start with what we know up until the value of 2n minus 3. Okay, and so that is how we can represent this function as a Maclaurin series. We have now identified the pattern for these terms after the first two and represented them as a power series, or more specifically, a Maclaurin series. Okay, now to make this a little bit more legible, I'm going to rewrite this a little bit. We'll have 1 times 3 times 5 multiplied up till 2n minus 3, and that will be multiplied by x to the power of n. All right, and then in the denominator, we have 2 to the power of n times n factorial. This right here represents our function f of x as a Maclaurin series. And remember that this series will be convergent for this interval of convergence. And so you could also say that that will be convergent on the interval from -1 to 1, including those endpoints. All right, so be sure to include that in your answer as well. That is the interval that power series or that Maclaurin series is convergent for. Okay, so hopefully you were able to follow each step of that process. I know things got a little bit hairy and a little bit messy when it came to representing those coefficients. So if that part was a little bit hard to understand, I would suggest that you go back and watch it again, and then if you have any questions, feel free to leave those in the comments. Okay, but with that, this was the last example for this lesson video. So if you want to see some more examples, I'll have an examples video on using binomial series to find Maclaurin series linked at the end of the video, as well as in the description below. If you have any questions, like I said, leave those in the comments below. But if you don't have any questions, this is all I had for now. So I will see you next time.